Hi there, in this video I'm going to show you how to prove this result. So the result being whenever you integrate 1 over the root of a squared minus x squared, a is a constant, okay? The answer being sine inverse x over a plus c. So remember, a is a constant. So to prove this result, so when proving a sine inverse result, we use substitution, okay, so we use substitution to derive this result, and take your substitution as x equals a sine theta. So to prove the sine inverse result here, we use substitution and we take our substitution to be a sine theta. When I prove the cos inverse result and the tan inverse related result, we use substitution also. So for the cos inverse result, x is a cos theta. For the tan inverse result, x is a tan theta. Okay, so we're going to use substitution here. So in step 1, I'm going to take x is a sine theta. Okay, so that is our substitution that we're going to use. That takes us to step 2 of substitution. Step 2 is to differentiate. So dx over d theta. A is a constant, bearing in mind. So when you differentiate sine, it's cos. So a cos theta. Let's rewrite this. Dx is a cos theta d theta. Okay? So let's have a think here. Okay, so let's focus on this integral. Let's take a red pen. Let's focus on this integral on the left. And let's prove that the integral on the left gives us this answer on the right. Okay, so let's have our eyes on this integral. Now, let's have a little think. Dx over here, we're going to replace by a cos theta d theta. And x is going to be replaced by a sine theta. Okay, when we go through the substitution process. So this takes us to step 3. So by substitution, so let's rewrite this integral that we have on the left hand side. Okay, so integration sign. Dx, as we discussed, we'll replace that by a cos theta d theta. And let's tick that term. So meaning that we've replaced that term. So let's tick that. Over the root of a squared minus, and x over here, we'll replace that by a sine theta. Don't forget to square. Okay? So let's simplify this. So we're going to have the integral of a cos theta on top divided by, now looking at this term under the root, so under the root, when we expand, we're going to have a squared minus a sine theta squared is a squared sine squared theta, okay, with respect to theta. Now let's have a look at these terms. So I have an a squared over here under the root, okay, which is common to both of these terms. I'm going to take a common factor. So I'm going to take a common factor of a squared out of the root. So if I take a common factor of a squared out of the square root, the root of a squared is a. Okay? So in the next step, I'm going to have the integral a cos theta on top divided by, if I take out a squared as a common factor out of the root, that will give me a into the root of 1 minus sine squared theta. Okay? Now, by doing this, I can cancel this a and this a, okay? And that takes us to step number 4. Now, when you do trigonometric substitution, my tip is mostly with trigonometric substitution, you're going to use a trigonometric identity at some stage of your substitution in order to simplify your calculation. So let me explain. So I have a root term over here. So we're going to be using an identity to help us. So the identity at this moment, we can use cos squared plus sine squared theta is equal to 1 in order to help us simplify the term within the integral. Okay, specifically this root term here. So if I rearrange, you might find that cos theta is going to be the root of 1 minus sine squared theta. So remember, when doing a trigonometric substitution, most likely you're going to be using a trigonometric identity to help you with the substitution process. Okay, so this is the identity that I've used. Cos squared plus sine squared is equal to 1, which when rearranged gives me this root term. The root of 1 minus sine squared we're going to replace by cos theta. So let's do that. So we're going to have the integral of cos theta on top over root of 1 minus sine squared is cos theta. By doing this, the two cos thetas will cancel, giving us 1 to integrate. And when we integrate 1, it's theta plus c. So if you integrate 1 with respect to theta, you're going to have theta plus c as a result. Okay? So we need to write theta back in terms of x, and in order to do that, go back to your substitution. X is a sine theta. Okay? So that is step number 5, the final step. So on the reverse, step number 5, since x is a sine theta, when I rearrange, a sine theta is going to be x, sine theta is therefore x over a, and theta on its own is the inverse sine x over a. So if we go back to the previous step, in step 4, we have theta plus c. So let's replace the theta by the inverse sine of x over a. So in this case, we're going to have the inverse sine of x over a plus c. Okay, so that is the result. So as you can see, that is the result of this integral, which we've proved using substitution, and the substitution, remember, is x is equal to a sine theta. Okay? So let me go through another result. So that was number 1, say. So we'll call that number 1. Okay? An inverse trigonometric related result. Here's another inverse trigonometric related result. So I'm going to call this number 2. So whenever you integrate, okay, minus 1 over the root of a squared minus x squared with respect to x, the result is going to be cos inverse x over a add c. Okay? So again, a is a constant in this integral. Okay? So in result number 1, we derived this using substitution, and x is a sine theta. In this result here, result number 2, we're going to use substitution also, and the substitution is going to be a cos theta. So let's let x equal a cos theta. So that takes us to step 2. So dx by d theta. When I differentiate cos, it's minus sine. So minus a sine theta. Okay. So dx will be minus a sine theta d theta. Okay. So in this case, let's have a stop and think. So over here, so again, if we focus on the integral on the left hand side, we can replace the dx here by minus a sine theta d theta, and the x by a cos theta. So let's take that and use that for step 3. So by substitution, so let's rewrite this integral on the left hand side. So integration minus, now dx, remember, first of all is minus a sine theta d theta. So we're going to have minus a sine theta d theta. So that is dx being replaced. So let's tick that off. Okay. Over the root of, and in this case we have a squared minus x in our integral is a cos theta. So an a cos theta, don't forget to square. Okay. So at the moment we have this integral to simplify. So let's simplify this. So it's the integral of minus into minus is a plus. So a sine theta in a numerator divided by the root of, and when we simplify the term with it under the root, we're going to have a squared minus a squared cos squared theta with respect to theta. Now I'm going to do the same as what I did in my previous derivation. So I had two a squared terms which are common to these two terms, and remember I took an a squared common factor out of the root. Now I'm going to do the same thing at this precise stage here. Okay, so I've got two a squared terms. A squared is common to both terms. So let me take a common factor of a squared out of the root. So I'm going to have, as a result, integration of a sine theta on top divided by taking a squared as a common factor out of the square root, that will give us a, root of a squared is a, and we're left with 1 minus cos squared theta. Okay, by doing this, the a's in the numerator and denominator will cancel, and this takes us to step 4. So step 4, remember what I said earlier, we need to use a trigonometric identity at some stage in order to help us with our substitution. Okay, so we need to think about a trigonometric identity specifically to help us with this square root term. So, and that identity is the same one as we used before. Cos squared plus sine squared theta is equal to 1. So if we rearrange this, sine theta will be the root of 1 minus cos squared theta. Okay, when you do your rearrangement. And if I replace the root of 1 minus cos squared theta in this integral by sine theta, we're going to have the integral of sine theta that we have currently on top divided by root of 1 minus cos squared is sine theta in the denominator with respect to theta. Now these two sine theta terms will cancel, giving us 1 to integrate with respect to theta. And when you integrate 1 with respect to theta, it's theta plus c. So now we need to rewrite theta back in terms of x, and as I did before, you need to go to your substitution in order to do that. So our substitution is x is equal to a cos theta. So let's continue on the reverse. Okay, so this is step number 5. So since x is a cos theta, a cos theta is x when I switch sides, cos theta is x over a, and that would make theta the inverse cos of x over a. Okay, so let's remind ourselves, currently in step 4 we had theta plus c, so if I replace the theta by the inverse cos of x over a, we're going to have the inverse cos x over a add c as our result. Okay, so as you can see, that's what we have over here. So we prove this result once again using substitution, and for the cos inverse related result, the substitution that you take is x is equal to a cos theta. Okay. Now let me go through the tan inverse related result. Let me prove another result. So let me prove the tan inverse result. So whenever you integrate 1 over a squared plus x squared with respect to x, the result is 1 over a tan inverse x over a plus c. So remember, a is a constant once again. And to prove this result, we use substitution again, and the substitution is a tan theta. Okay, so let's derive this result using substitution. So in step number 2, dx by d theta, so a is a constant bearing in mind, and when we differentiate tan we get sec squared, so it's a sec squared theta. Dx is going to be a sec squared theta d theta. So once again, if you focus on this integral on the left hand side, we can replace the dx here, highlighted in green, by a sec squared theta d theta, okay? And the x over here, will replace that by a tan theta. So that takes us to step number 3. So by substitution, let's rewrite this integral, okay? So integration of dx, as we discussed, is a sec squared theta d theta. So dx has been replaced, so let's tick that. And we have divided by, and the remaining term in the denominator is a squared plus x, and x over here is a tan theta. So a tan theta, don't forget to square. Okay, so let's expand these brackets within the integral. So we have the integration of a sec squared theta on top divided by a squared plus a tan theta with a squared is a squared tan squared theta. Okay, now at this stage I'm going to take a common factor of a squared from the denominator. So in the numerator I have currently a sec squared theta, and if I take a common factor of a squared in the denominator, I'm going to be left with 1 plus tan squared theta. Now that takes us to step number 4. So step number 4 is the choice of the identity. Okay. Now remember what I said earlier twice, or maybe more than twice. I've said that when you use a trigonometric substitution, most likely you'll be using a trigonometric identity at some stage, okay, of the process. Now we need to use an identity here, and the identity for us at this stage is 1 plus tan squared theta is equal to sec squared theta. So this is the identity for us, okay? So let's replace the 1 plus tan squared theta here by sec squared theta. So we're going to have the integration a sec squared theta on top divided by an a squared, and 1 plus tan squared theta is sec squared theta. Okay, now by doing this, the 2 sec squared theta terms will cancel, and one of the a terms will cancel below. So we're left with 1 over a, so be careful, 1 over a is left over to integrate with respect to theta. And when you integrate 1 over a is a constant, with respect to theta, we're going to have 1 over a theta plus c. Okay, so we need to write this back in terms of x, and remember, go back to your substitution. X is equal to a tan theta in order to write this back in terms of x. Okay, so that is step number 5, final step. So since x is a tan theta, so a tan theta is equal to x. Tan theta on its own is x over a, and that makes theta the inverse tan of x over a. Okay, so if I go back to step number 4, we had 1 over a theta plus c. If I replace this theta by the inverse tan of x over a, this is what we're going to have. We're going to have 1 over a inverse tan x over a add c. So as you can see, this is what we had exactly on the right hand side. Okay, so this is a derivation of this trigonometric inverse related result for tan inverse, and we've derived that using substitution again. Okay, so that ends this video. I hope you enjoyed this video. If you did enjoy the video, a like is very much appreciated, and I hope to see you again. Thank you.